Now we have derived the formula for the logarithmic decrement in previous session as delta is equals to 2 pi zeta upon root of 1 minus zeta square, So I want to find out the value of zeta in terms of delta now. So I want to write this equation in terms of zeta, damping factor. So squaring on both sides. So what we'll get? Let us see. Delta square is equals to 4 pi square zeta square divided by 1 minus zeta square. So I will take this 1 minus zeta square on left hand side. So delta square minus delta square zeta square is equals to 4 pi square zeta square. I will take the zeta term on right hand side. So delta square is equals to 4 pi square zeta square plus delta square zeta square. Taking zeta square common on right hand side, so 4 pi square plus delta square into zeta square is delta square. So the formula or the value of zeta square will be delta square upon 4 pi square plus delta square, or you can write the value of zeta as delta upon root of 4 pi square plus delta square. So this is the formula of damping factor in terms of logarithmic decrement. So in this session we are going to discuss about another formula for logarithmic decrement. So in this case I have shown the displacement versus time plot for a damped free vibration. So the amplitude of vibration is reducing in every cycle. Let us consider x0 as the starting amplitude. The successive amplitude is x1, then x2, x3, so on. So we will consider x suffix n as the amplitude of nth cycle, nth cycle. So over here you need to remember that for starting position I have taken the amplitude as x0 instead of x1. The starting amplitude over here is taken as x0. So if I want to find out the logarithmic decrement is given by the natural logarithm of the ratio of any two successive amplitude considered on the same side of the mean position. So all these amplitudes x0, x1, x2, x3 are considered on the same side of the mean position. So above the mean position I have considered all the amplitude. So if I want to write down this delta value, it can be written as x0 upon x1, or we can write this as log to the base e x1 upon x2. Also it can be written as log to the base e x2 upon x3 and so on. So we can write this formula for nth cycle as log to the base e xn minus 1 upon xn, minus 1 upon xn. So for n number of cycles, we have written the formula for this logarithmic decrement. So if I am going to add all these, logarithmic decrement, so there are such a 1, 2, 3, 4, n number of delta values. So the total of these will be n into delta. The total, if I am going to do the addition, will be n into delta. So that n into delta will be log to the base e x0 upon x1 plus log to the base e x1 upon x2 plus log to the base e x2 upon x3 and so on. So at the end you will get log to the base e xn minus 1 upon xn. So we know log a plus log b is log of a into b. So using that formula, n into delta, you will get log to the base e x0 upon x1 into x1 upon x2 into x2 upon x3 so on, plus, sorry, not plus, into xn minus 2 upon xn minus 1 into xn minus 1 upon xn. So you can see over here the term x1 x1 x2 x2 x3 x3 xn minus 1 xn minus 1, all these terms will get cancelled and we will get n into delta equals to log to the base e into bracket x0 upon x0 upon xn, x0 upon xn. So we can write the formula for delta. Delta is equals to 1 upon n log to the base e x0 upon xn. So here we have got the formula for logarithmic decrement for n number of cycles as delta is equals to 1 upon n log to the base e x0 upon xn. So n represent the number of cycles, x0 represent the starting amplitude, xn represent the amplitude of nth cycle. So in this numerical, mass is given as 20 kg. Now it is been given that 50 oscillations are observed, and for that 50 oscillations time required is of 20 seconds. 20 seconds. And also it is given that the amplitude of vibration decreases to 1/4 of the initial value after 4 oscillations. So number of oscillations are given 4 and the amplitude of oscillation of the fourth cycle is 1/4 of the initial. So initial amplitude we are considering as x0. So 1/4 of the initial amplitude is the amplitude of fourth cycle. So this is the given data for this numerical, and we need to find out the logarithmic decrement, the damping factor and the damping coefficient. So let us start with the logarithmic decrement. Now for 4 cycles, the data is given. So the formula for logarithmic decrement that we are going to use is 1 upon n into log to the base e x0 upon xn. So here n is 4, so delta is equals to 1 upon 4 log to the base e x0 upon xn. So what is the value of x0 upon xn then? X0 upon x4 is 4. So the value of delta is equals to log, natural log of 4 divided by 4. So delta is 0.346. The value of delta is 0.346. Now we'll try to find out the damping factor. So we have written the formula of damping factor in terms of the logarithmic decrement. So zeta is equals to delta upon root of 4 pi square plus delta square. So delta value is 0.346 divided by under root of 4 pi square plus 0.346 square. So solve this, you will get the value of zeta. So the value of zeta is 0.0549. The value of zeta is 0.0549. Now we need to find out the stiffness of the spring. We need to find out the stiffness of the spring. So the stiffness of the spring, if it is asked, then first of all we will need to find out the value of frequency. So here it is given that the time taken to complete 50 oscillations is 20 seconds. So we can find out the frequency for damped vibration from this. So you know very well, frequency is nothing but cycles per unit time or number of cycles per unit time. So here there are 50 oscillations. So the frequency is 50 divided by 20, that is 2.5 hertz. The frequency of damped vibration is 2.5 hertz. So you can find out the value of natural circular damped frequency from this. So the natural circular damped 2 pi into the frequency of damped vibration. So 2 pi into FD is 2.5. So 15.707 radian per second is the natural circular damped frequency. Now find out the value of omega n, that is natural circular frequency. So the natural circular frequency omega n, it is given, or the value of damped circular frequency omega t is given by formula root of 1 minus zeta square into omega n, root of 1 minus zeta square into omega n. So 15.707 is equals to root of 1 minus 0.0549 square into omega n. So find out the value of omega n. So omega n is 15.73 radian per second is the natural circular frequency. So if I want to find out the value of stiffness, spring stiffness, so omega n is root of k by m. So find out the value of k from this. So 15.73 is equals to root k upon m. Mass is given as 20 kg. So find out the value of k. So it is 4949.11 Newton per meter. 4949.11 Newton per meter. And now we want to find out the value of the damping coefficient or the value of C. So we do know that the formula for zeta is C upon Cc. It is equals to C upon twice m into omega n. So zeta is known to you. Zeta is 0.0549 is equals to C upon 2 m is 20 into omega n is 15.73. So find out the value of C. So C is 34.54. 34.54. Unit is very important. Newton second per meter. Newton second per meter.